Okay. Um, yeah, I have over 600 subscribers now. That makes me happy. Uh, I guess I'll just keep doing this. Okay. Let's see. Where did we leave off at? Ah, yeah. So last time, we actually made a quick kernel modification to pretty much print out the scheduled entity, which is like the task that gets pulled off from the run queue to run. And we wanted to actually look at what specific tasks were. So we actually ended up writing code to print out some logging on the name and the v runtime of that specific scheduled entity, which is associated with the task. What ended up happening was that I think this print k kind of makes everything run slower, so it just uh, never really finishes. I didn't even leave it running at all. I just decided to kill it and yeah, move on. I think we know what we. I think we can see that like the whole point was like we wanted to see what what v runtime looked like, and it was just some really big number. So yeah, I think we learned a lot just from that, and I personally think that it's time to just comment all this out. So we just did this. I think, oops. How do I do that multi-selecting in things like control? Oops. Ah, come on. Okay, I know this. So if we were to do control V, shift V, shift I, that, that. No, that's not how we do it. Uh, I know this. There we go. Control V, shift I. Okay, so we comment all that out. Um, we'll get back to a good state. I'm going to rebuild the kernel right now, just while we're studying, so that um, we don't have to wait too long. This is back at the original built-in kernel right now, so that's why everything's like working just fine. So just need to make J. I'll just be more realistic. 48, and I'll just let that go to fix ourselves, and then let's just continue reading. Okay, so we last left off here. Okay, so note that pick next entity does not actually traverse the tree to find the leftmost node because the value is cached by RB leftmost. So this attribute stores the leftmost node. Although it is efficient to walk the tree to find the leftmost node, which is going to be O height of the tree, O log n for n nodes. If the tree is balanced, it is even easier to just cache the leftmost node. The return value from this function is the process that CFS next run. If the function returns null, then there is no leftmost node and no nodes in the tree. In that case, there are no runnable processes, and CFS schedules the idle task. So there is still always some sort of task to run. In Linux, it's just called the idle task. It's a special task. I think it's PID 0 from what we read before. So okay, so adding processes to the tree. Now let's look at how CFS adds processes to the RB tree, so the red-black tree, and caches the leftmost node. This would occur when a process becomes runnable, meaning that it wakes up, or when it's first created via fork, as discussed in chapter 3. So, like when you remember, when we first fork a process, that process runs immediately because we want to give it an immediate chance to exec into something else. Because of the way how memory is like shared, it's like kind of lazy. We want to make sure that, and most of the time, um, things that call fork, the child process will just exec into something else anyway. So anyway, adding process to the tree is performed by the enqueue entity function call. So enqueue entity takes in the run queue, the pointer to the run queue, and then the scheduled entity of that task, and then some flags. So that's how we queue up a new scheduled entity. Let's see. Update the normalized v runtime before updating min v runtime to calling update cur. So I think this is a typo. Opportunity for a pull request if you were in 2010. Okay. Anyway, so flags in queue wake up or flags in queue migrate. I guess you just do something here. Otherwise, you will update the runtime statistics of current. So update the current, I guess, run queue, entity in the run queue. All right. Update stats is another function call. Okay. And then finally, this is the one I think is to just and finally stick in the scheduled entity to the CFS run queue. So this double underscore enqueue entity. So this function updates the runtime and other statistics and then invokes enqueue entity to perform the actual heavy lifting of inserting the entry into the red black tree. So this is what it is. This is the heavy lifting thing. Let's actually look at in, I guess, syntax highlighted code. It might be easier. So yeah. So we do double underscore enqueue entity, and we'll search for all the declarations. So right here. So static void enqueue entity. So we take in, so that's link. I don't know what that is. Parent is null. Schedule, and also it's creating a new RB node. Okay. So schedule entity entry. Okay. Key. So it's gonna create the key for this scheduled entity. My guess is that it's going to just do that v runtime as a key. Leftmost one. Okay. So find the right place in the red black tree. So sketch entity is going to be the type. The run node is, what is this? Oh, this is, again, I remember now. This is actually a macro. So, okay. So what is run node? Run node. Interesting. Well, parent is probably the parent pointer, so null. Okay. We don't care about collisions, nodes. So we want to find the parent entry, and then we want to do that link. Okay, sure. Okay, so if key is less than the entity key of the current entry, because entry is going to be the current red black tree entry from the parent node here, right? We want to go left, otherwise we go right. And then, of course, when we go right, we have to flip this leftmost flag to 0 because it's no longer leftmost. The second we move right, it's no longer considered leftmost. Obvious reasons. Okay, so now once you've finally figured out a place to link or insert into the tree, okay, you want to then set the RB leftmost to be the node that we're at. Okay, and then okay. So reading this RB entry run node is just the property of the SE. Okay, so that's the macro. What is a property and what is the type? So then the parent node, the property or the type of the entity, and then the run node or the property of that type. Okay, whatever. Okay, so once you found link, so this is the right place to insert into the tree. You want to basically connect run node and link together, and then RB insert color is probably the red black tree stuff here, which is going to either make the node red or black and then rebalance the tree. So we'll probably touch on that some other chapter. But that's what it does. So it's just like a regular. So this enqueue entity is really just like a normal red black tree insertion. And it's just inserting scheduled entities. So I want to see what RB link node is. So if I were to where would I find that? Let's see, RB link node. It should be defined in like RB tree or something like that. So okay, RB link node. Oops, jeez, I just triggered. Okay, all right. Um, Start from the top. RB tree. So we have static inline void RB link node. So we go here. It's as simple as taking the node. Okay. Parent color. Okay, setting the parent color property. Setting its left and right to null, and then just assigning that link node to the current node being passed. Okay, so there is a reason why. Like, notice how these nodes are not exactly like they're just very simple pointers with a left, right, and a parent. They don't actually contain data. It's actually so it's actually the data structure that will contain this link, not really the link contains also the data structure and the pointer to the next node. Like the way we normally think of in terms of like nodes, right? So don't worry, we're gonna explain that soon. It took me a while to actually kind of visualize that too. So anyway, just take this as like a normal. I mean, the way I'm seeing this right now is this is just normal tree insertion. Okay. Um, yeah, and like the thing that screams normal tree insertion here is this right here. If the key is less than whatever current node, then go left. Otherwise, go right. So anyway, let's look at this function. The body of the while loop traverses the tree in search of the matching key, which is the inserted process's v runtime. So it's the key is comparing the v runtime of things. So okay, and it's traversing while it's not null. Okay, so per the rules of the balanced tree, it moves to the left child if the key is smaller than the current node's key, and to the right child if the key is larger. If it ever moves to the right even once, it knows the inserted process cannot be the new leftmost node, and it sets leftmost to 0. If it moves only to the leftmost remains true when it remains 1, right? And we have a new leftmost node and can update the cache by setting RB leftmost to the inserted process. The loop terminates when we compare ourselves to a node that has no child in the direction we move. Link is then null and the loop terminates. So here is link. Link is going to be that child, the potential pointer. When out of the loop, the function calls RB link node on the parent node, making the inserted process the new child. The function RB insert color updates the self-balancing properties of the tree we discussed coloring in chapter 6. Okay. Removing processes from the tree. Finally, let's look at how CFS removes processes from the red-black tree. This happens when the process blocks, becoming unrunnable, or terminates, ceases to exist. So when let's say IO request came in, the process has to, it's blocked on something, so it has to get out of the tree because again the red black tree is pretty much the run queue. So yeah, let's look at it in color. So DQ entity right here. So okay, so if we have a leftmost node and it is the run node, okay, next node is going to be RB next, left node next, RB erase. That's probably to just remove it. Remove this current node right here from the run queue. I really don't know what task timeline is. We'll probably see. Let's see. Well, we'll look at it later, but it looks to be much smaller than NQ. Okay, oops. Back here. Um, so this is all stat stuff, and then the big stuff is going to be this one. Okay, and we just looked at that function. So as with adding a process to the red-black tree, the real work is performed by a helper function, Thunder DQ entity, right here. Removing the process from the tree is much simpler because the RB tree implementation provides the RB erase function that performs all the work. The rest of this function updates the RB leftmost cache. If the process to remove is the leftmost node, the function invokes RB next to find what will be the next node in an in-order traversal. Okay, it finds an in-order successor to be the new next node in the tree. This is what will be the leftmost node when the current leftmost node is removed. Okay. The main entry point into the process schedule is the function schedule defined in kernel schedule.c. Okay, let's go there. Let's see. Kernel schedule.c. Let's see. Right there. And then schedule. Do we have one? Schedule debug. Schedule. Ooh. Jeez. This looks intimidating. I already see ASM linkage, which is like assembly maybe. Okay, let's read into that more. This function that the rest of the kernel uses to invoke the process scheduler, deciding which process to run and then running it. Schedule is generic with respect to scheduler classes. That is, it finds a highest priority scheduler class with a runnable process. So remember, based off of whatever process, we can have multiple scheduler classes. CFS is just one of them. We also have a real-time one. So, or I don't think it's truly real-time, but real-time like one. Yeah, and ask what to run next. So it picks the scheduler class, and then it finds a runnable process inside that scheduler class. So, given that, it should be no surprise that schedule is simple. The only important part of the function, which is otherwise too uninteresting to reproduce here, is its invocation of pick next task, also defined in kernel schedule.c. The pick next task function goes through each scheduler class, starting with the highest priority, and then selects the highest priority process in the highest priority class. Okay, so again, two layers here. The scheduler class, and then each class has a process. So first, pick the highest priority scheduler class. Could be CFS, could be real time, could be whatever. And then pick the highest process in that class to decide what to run. So pick next task is this thing here. Okay. So basically, schedule class is any one of the scheduler classes. I wonder if we can see the definition here to see what's in there. Yeah, let's do that. So before we do that, let's do let's do this. Schedule class. So construct schedule class. That's declaring it. Okay. Probably in schedule H. Let's see, schedule.h. So let's ask the LM. Let's see. Do it again. Okay, schedule H. Jeez. Okay, then sketch class. Right there. So the sketch class, this looks like an interface, right? So looks like these are a bunch of macro. That is a macro. It defines a bunch of these functions to run. Sure. So things like, for example, enqueue task, dequeue task, these are function pointers. Remember this syntax here, the name of the function with the pointer and then the argument list right here. Okay. Pick next task. We saw that. We know that. And then, yeah, so that's what it looks like. It looks like an interface. It's just like CFS and all the other types of schedulers are probably kind of like providing their implementation through the function pointers. And maybe that's how it all works. Okay. So yeah, this a schedule class is expected to have this pick next task function implemented and pointed to the right place. And it has to implement a signature where there's only one argument and that is a run queue. So like if we were to go back to this class schedule class definition here, we could see that if we looked at pick next task, I'm not sure where that is. Put pick next task right here. See how it only accepts one argument, which is the pointer to the run queue. So yeah, so it's fair sketch class pick next task. Blah blah blah. Okay. What's this? We know that if all tasks are in the fair class, we can call that function directly. Oh, okay, cool. So note that the optimization at the beginning of the function, because CFS is a scheduler class for normal processes and most systems run mostly normal processes, there is a small hack to quickly select the next CFS provided process if the number of runnable processes is equal to the number of CFS runnable processes. So you can make the assumption that if the number of processes in the system is equal to the number of CFS processes, right? So right here, this condition here, which is likely going to happen, likely meaning that's a compile optimization to do stuff because you're kind of like confident that this branch is always going to hit, right? So the number of processes running is equal to the number of processes in CFS running. Make the assumption that pretty much you're only caring about CFS now because all the processes belong to the CFS scheduler. So, okay. The core of the function is the for loop, which iterates over each class in priority order, starting with the highest priority class. Each class implements the pick next task function. So each class implements the pick next task function. So remember, this was just a function pointer. If you are creating like a new scheduler class, we have to actually implement this ourselves. That would be fun, right? Like let's create like the worst scheduler class possible, like just like a simple round robin, go against the whole like time the proportion of the CPU thing and just reintroduce time slices again. Which returns a pointer to its next runnable process, or if there is not one, null. The first class to return a non-null value has selected the next runnable process. CFS's implementation of pickNextTask calls pickNextEntity, which in turn calls pickNextEntity function that we had discussed in the previous section. So it all just leads back to whatever we've seen before. Okay. So tasks that are sleeping or blocked are in a special non-runnable state. This is important because without the special state, the scheduler would select tasks that did not want to run or worse, sleeping. Okay, so tasks are sleeping, meaning that they are blocked, are still considered non-runnable. Okay, why? Because let's see, yeah, sleeping would have to be implemented as busy looping if we don't consider them to be unrunnable. A task sleeps for a number of reasons, but always while it is waiting for some event. The event can be a specified amount of time, more data from a file I/O, or another hardware event. A task can also involuntarily go to sleep when it tries to obtain a contented semaphore in the kernel. This is covered in Chapter 9, Introduction to Kernel Synchronization. A common reason to sleep is file I/O. For example, the task issue a read request on a file which needs to be read in from disk. As another example, the task could be waiting for keyboard input. Whatever the case, the kernel behavior is the same. The task marks itself as sleeping, puts itself on the wait queue, and removes itself from the red-black tree of runnable and calls schedule to select a new process to execute. Whew. Okay, so let me digest that. Okay, so okay, so there are two queues, right? Two queues. So we know one already called the run queue, which is that RQ thing, that the RB tree. Then we also have a wait queue. Okay, so basically, when a task T1 wants to make some sort of call to a file store, it has to then one what was it marks itself as waiting, right? Yeah, marks itself as sleeping. Okay, marks itself as sleeping, which means it is non-runnable. Okay, and then two, what does it do? It puts itself in a wait queue. Okay, so in queues itself into the wait queue. Okay, and finally removes itself from the run queue. Okay, so that's when the task wants to make some sort of IO, right? IO request. Because then it's blocked now, waiting for this one to kind of just finish in this case. So it's going to say sleeping, non-runnable, no longer runnable. Then it queues itself into a wait queue and then removes itself from the run queue because the run queue only contains running processes. And then what happens next? Okay. And calls schedule to select a new process to execute. Okay. So then new process is selected to run in place of current task. Okay, so that's the pattern. So given a task that becomes blocked, it needs to mark itself as sleeping or unrunnable. It then queues itself, so it adds itself into the wait queue. Then it removes itself from the run queue, and then pretty much new process is selected to run in place. Okay. So waking back up is the inverse. The task is set as runnable, removed from the wait queue, added back into the run queue. As discussed in the previous chapter, two states are associated with sleeping: task interruptible and task uninterruptible. They differ only in that tasks in the task uninterruptible state ignore signals, whereas tasks in the task interruptible state wake up prematurely and respond to a signal if one is issued. Okay, both types of sleeping tasks sit on the wait queue waiting for an event to occur and are not runnable. Okay, so wait queue in this case has two tasks, two states. Okay, task uninterruptible and tasks that are interruptible. So two types of non-runnable tasks. Okay. Wait queues. Sleeping is handled via wait queues. A wait queue is a simple list of processes waiting for an event to occur. So it's a simple list. Wait queues are represented in the kernel by wait queue head T. Wait queues are created statically via declare wait queue or dynamically via init wait queue head. So it's a linked list. So not, I don't think it's the same as a red black tree in this case, just a regular linked list. Processes put themselves on a wait queue mark themselves not runnable. When the event associated with the wait queue occurs, the processes on the queue are awakened. It is important to implement sleeping and waking correctly to avoid race conditions. Some simple interfaces for sleeping. Hold on. Okay. So some simple interfaces for sleeping used to be in wide use. Some simple interfaces for sleeping used to be in wide use. What does that mean? Like there was different ways to sleep in the code base. Let's see. These interfaces, however, have races. It is possible to go to sleep after the condition becomes true. In that case, the task might sleep indefinitely. Therefore, the recommended method for sleeping in the kernel is a bit more complicated. Okay? Hmm. Q is the wait queue we wish to sleep on. So define wait, add to wait queue. So this is the wait queue, and then this is the task to be waited on. So while some condition, so the condition is, so while the condition is not true, okay, and the condition is the event we are waiting for, we want to what? Prepare to wait. So we want to be task interruptible. I think task uninterruptible is actually a rare state to be in. Then okay, so we schedule the next task. Sure, and we finish wait. Okay, so define wait will create a new wait queue entry given this data. So it adds itself to wait queue via add wait queue right there. This wait queue awakens the process when the condition for which it is waiting occurs. Of course, there needs to be code elsewhere that calls wake up on the queue when the queue event actually occurs. Okay. Calls prepare to wait to change the process state to either task interruptible or task uninterruptible. This function also adds a task back to the wait queue if necessary, which is needed on subsequent iterations of the loop. Okay, so prepare to wait also adds back to the wait queue if necessary. Not sure what that means. If the state is set to task interruptible, a signal wakes the process up. Okay, this is called the spurious wake up. A wake up not caused by the occurrence of the event. So check and handle signals. Oh, okay. So this is to stop the task from sleeping indefinitely. So periodically, like even if the event hasn't occurred, there's gonna be a check for any signals. Okay. So when a task awakens, it checks whether the condition is true. If it is, it exits the loop. Otherwise, it calls schedule again and repeats. So right there. Okay, now that the condition is true, the task sets itself to task running and removes itself from the wait queue via finish wait. So finish wait is right there. Removes itself, puts it back into the running queue. If the condition occurs before the task goes to sleep, the loop terminates and the task does not erroneously go to sleep. Note that the kernel code often has to perform various other tasks in the body of the loop. For example, it might need to release locks before calling schedule and reacquire them after or react to certain events. Okay, so if the condition has occurred before the task has gone to sleep, So this would not actually be true. So then we just take it out of the wait queue. Oh, so that's protection right there. Putting the taking out of the wait queue outside of the while loop. Okay. The function iNotify_read in fs notify iNotify user, which handles reading from the iNotify file descriptor, is a straightforward example of using wait queues. Okay, so let's read that in code. So fs iNotify user.c. So iNotify user.c. What do we get there? Okay, so then what is it? iNotify read. Oops. Okay. So how is this a simple example? Oh, it's the same thing right here. So we define wait. So we create that wait queue entry, and then we have a while loop that prepares to wait. It does all this locking and all this file system related things. Okay, and then it has a signal pending thing, which I think is similar to this one up here. Signal pending, right? And then in this case, if there's a signal pending, we break from that loop. Otherwise, then let's call schedule again. Okay, and then if the condition is met or like we break out of the loop, we'll just remove from the wait queue here. So it's like a application of this pattern. Okay. This function follows the pattern laid out in our example. The main difference is that it checks for the condition in the body of the while loop instead of the while statement itself. So that's the reason why it's an infinite loop. This is because checking the condition is complicated and requires grabbing locks. This specific condition, this one, it needs to obtain locks and things like that to check, which is why it doesn't have a simple condition check here. It just breaks whenever it's no longer relevant to run. Okay. Okay, so the loop is terminated via break. So we use breaks to get out, not checking for the condition. So when we get out of that loop, oops, sorry. When we get out of that loop, then we'll basically call finish wait. Cool. So waking up. Waking is handled by wake up, which wakes up all the tasks waiting on the given wait queue. It calls try to wake up, which sets the task state to task running. Calls on queue tasks to add the task to the red-black tree, and sets need rescheduled if the awakened task's priority is higher than the priority of the current task. Okay, if the awakened task priority is higher than the priority of the current task, need reschedule. The code that causes the event to occur typically calls wake up itself. The code that causes the event to occur, okay? For example, when data arrives from the hard disk, the VFS calls wake up on the wait queue that holds the processes waiting for data. So once data arrives from the hard disk, VFS will then calls wake up for all the processes waiting for that data. So the processes are in the wait queue constantly checking for that condition. VFS will notify these processes. Okay. An important note about sleeping is that there are spurious wake ups because of the signal checks. Because just because a task is awakened does not mean that the event for which the task is waiting has occurred. Sleeping should always be handled in the loop that ensures that the condition for which the task is waiting has indeed occurred. Figure 4.1 depicts the relationship of between each scheduler state. So, task running. This is our task that is running right now. Okay, it's runnable. When's it happening? Well, adds to the wait queue, adds task to the wait queue, sets a task state to task interruptible, and then calls schedule. Schedule calls deactivate tasks, which removes the task from the run queue. So this is the part that actually removes the task that has just transitioned from runnable state to interruptible state. Away from it takes it out from the run queue. This is the thing in charge. Not obvious to me. So once you have that, periodically, right? You're interruptible. You're waiting. Periodically, you'll receive a signal, and then you're running just temporarily, and you're adding yourself back to wait queue again. Or if the event occurs, right, then you basically try to wake up, set your task for running, activate the task back to the run queue, and then call schedule again, and then the entries are removed from the wait queue. So this might happen like way more often than this if the condition is going to take a while. So it's always going to be back into some running state after some period of time. And spurious, meaning that it's like random, just based off of some signals. Yeah. So now let's go on to preemption and context switching. Context switching, okay, the switching from one runnable task to another is handled by the context switch function defined in kernel schedule.c. It is called by schedule when a new process has been selected to run. It does two basic jobs. First, calls switch mm. I think mm was like memory manager. Yeah, which is declared in ASM MMU context H to switch the virtual memory mapping. Oh, memory map. Okay, from the previous processes to that of the new process. So switch the memory map and then call switch to switch the processor state from the previous processes to the current. This involves saving and restoring stack information and the processors registered in any architecture specific state that must be managed and restored on a per process basis. Okay, so remember that again, like really bad diagram. So let's just pretend this is like a context switch example. So we have some sort of virtual CPU, right, that models that of a real CPU. So we'll have a real CPU. So we'll just have x86 CPU. Actually, let me make that bigger. Okay. So the switching is what they're saying. So we have a vCPU. That's just like the software version. OS software model of CPU. So this has like a stack, then the registers, and that like kind of maps to the real CPU, right? So the CPU has stack, registers. Okay. So this is like pretty much mapping of this. So this is like the software model of the real CPU, and basically it's per task, right? So task one has one of these, task two has another vCPU, right? That has stack here in reg. Okay, so at some point when a context switch occurs, what ends up happening is that, well, this is no longer the active vCPU, but instead this one becomes mapped to the CPU. So what ends up happening is that in the context switch is that all this junk here currently gets saved. Save CPU, reg, stack and reg to current task vCPU. And then after that, load next tasks vCPU, stack, and reg to CPU, right? So first, when we switch from task one to task two, all of the current CPU stack and registers gets saved back to whatever the struct. This is a struct, right? This is the task structs, right? Just pretend. All that physical values get stored back into memory for like that mirrors the stack and registers here. Then you take this one from memory, right? This task from memory, load it, stack, and register in memory back to the physical CPU. So then that's how you create that illusion of like having a task think that it's the only one running on the machine. Okay. So the kernel, however, must know when to call schedule. If it called schedule only when code explicitly does so. So right now we've only seen schedule being called explicitly, right? But the kernel has to be smart enough to know when to call that too. So if 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 it called schedule only when the code explicitly does so, user space programs could run indefinitely. Instead, the kernel provides the need reschedule flag to signify whether a reschedule should be performed. See table 4.1. This flag is set by scheduler tick when a process should be preempted and by try to wake up, which is another function call. Okay, when a process that has a higher priority than the current running process is awakened, okay, when a process that has a higher priority than the currently running process is awakened, the kernel checks the flag to see that it is set and calls schedule to switch to a new process. Okay, so process wakes up. Okay, it has a higher priority than the current running process. Reschedule will happen so that we switch that new awakened process. This flag is a message to the kernel that the schedule should be invoked as soon as possible because another process deserves to run, right? Because the higher priority process has just awakened. So okay. So functions for accessing and manipulating need reschedule. So that changes the flag. Set TSK need reschedule. So sets the need reschedule flag in the given process. Clear task need reschedule. Clear the need reschedule flag in a given process. Need reschedule will test the value of the need reschedule flag. Return true if set, false otherwise. Okay. Upon returning to user space or returning from an interrupt, the need reschedule flag is checked. If it is set, the kernel invokes the scheduler before continuing. Okay. The flag is per process and not simply global because it is faster to access a value in the process descriptor. The flag is per process and not simply global because it is faster to access a value in the process descriptor. Okay. Then a global variable. Historically, the flag was global before 2.2 kernel. In 2.2 and 2.4, the flag was an int inside the task struct. In 2.6, it was moved into a single bit of a special flag variable instead of the thread info structure. Inside the thread info structure. Okay, so where is this at again? Context switch function in kern schedule.c. Okay, let's look for it. We're in schedule.c. No, we're not. Oops. Schedule.c. Okay, we're gonna go context switch. Void wait task context switch. Nope. This one static inline void context switch. So you have the current run queue, you have the previous task, and you have the next task. Then you'll have the memory map, right? So you have the new memory map and the old one. So prepare, blah blah blah. So okay, so the old memory map was the previous active one. And then the memory map that's going to be current is going to be the next memory map right here. You see this? Okay. Based off of architecture, start the context switch with previous, meaning that it's probably going to draw out the registers in the stack from physical, I guess, PCPU into the previous. Likely this is going to happen. Okay, so the active memory map for next one is going to be the old one. I guess do the atomic operation, atomic increment. I don't know yet. Does all this memory switching things. Okay. Okay, so it really does sort of what we kind of assume. It switches like memory maps. Here we just switch the register state and the stack. So switch to preep, next preep. Not sure what this is, but it reads like what we would assume. And then this run queue must be evaluated again because preep may have moved CPU since it called schedule. Thus, the run queue on its stack frame will be invalid. Sure. Okay. Finish task switch is the last thing. So it does move like memory stuff around. Um, that fixed me. Do we need to worry about run queue being invalidated by the task switch? A schedule tail though. We're only concerned with this. Okay. I'm gonna stop here. Let's see if this is done. And it is. So wait, error, undeclared. Oh, I commented too much out. Let's fix that real quick. This is sketch.c, right? So average dev. No, what? Sketchfair.c. Okay. Okay. Right here. So we don't need to comment this out. Okay, and yeah, I'll just build that and we should be back into the 2.64 kernel. Okay. That's it. Thank you.